Okay, we have a heat treating process here where I throw a 1 kilogram metal part, which has a specific heat given here. It's initially at 1075 Kelvin. Okay, I throw that into a huge insulated tank of water with 100 kilograms of water in it with a specific heat of that. And you can see the specific heat of water is like 9 times bigger than the specific heat of the metal. That means it's going to take more energy to raise the water than it does to raise the metal. Anyway, the water's initially at 295 Kelvin. It wants me to find the final equilibrium temperature. So again, we're going to use specific heats here. Again, we do that with incompressible substances like metal. Certainly for the metal we would, because we do not have tables. For the water, we could approximate the energy of water based on the temperatures of water as a saturated liquid. But because they gave us the specific heat and because we're using metal specific heat, we'll use that. But again, we could for water use saturated liquid at the temperature as an approximation for the energy of liquid water. Okay, but bottom line is what we're going to do here is we're going to apply our first law equation, which again is going to be delta U plus delta KE plus delta PE equals Q minus W. First off, we can get rid of our kinetic energy and our potential energy. We almost always get rid of that. Most of the problems in thermodynamics do not contain kinetic energy or potential energy. Now, Q is also 0. Okay, the tank is insulated, which means it's adiabatic, which means there's no heat loss to the surroundings. There is definitely heat transfer between the metal and the water, but again, we're defining our system as both the water and the metal. Okay, so it's not that there's not heat transfer between them, it's that there's none to the surroundings. In addition, because these are both incompressible, there's no change in volume, there's no paddle wheel, there's no mixing, anything like that. The work also goes to 0. So really all I've got is that delta U equals 0. Okay, so now you'll remember for using specific heats, the change in U is going to be C times the change in temperature. So for the metal part, it's going to be the mass of the metal times the specific heat of the metal times T final minus T initial of the metal. Okay, and keep in mind water, they'll eventually come to equilibrium, so they're going to have the same final temperature. That's why I just call this T final. So that is the change in energy of the metal. Change in energy of water is the mass of the water times the specific heat of the water times T final minus T initial of the water. So that's the change in energy of the metal. This is the change in energy of the water. Those two added together have to equal 0. So essentially, the temperature of the metal is going to drop. The temperature of the water is going to go up until the energies reach equilibrium because everything else goes to 0. So I just start plugging in numbers. So we got 1 kilogram, a half a kilojoule per kilogram Kelvin. That's the specific heat. T final, and then T initial is 1075 for the metal. Water has 100 kilograms. Specific heat of 4.4 kilojoules per kilogram. T final minus T initial, which is 295. That equals 0. So through the magic of algebra, I can solve for T final, and I find T final equals 295.5 Kelvin. And again, that makes sense for 2 reasons. First of all, I have 100 times more water than I do metal, so the water can absorb a lot more just because there is a lot more water. In addition, the specific heat of water is much larger than the specific heat of the metal, meaning it's going to take more to get a temperature change in the water than it is in the metal.